Joe, did you hear me?
Yeah. Do number 2?
No, number 2 seemed pretty straightforward. I don't think any of you would have trouble with that, but the other problems seem to cause trouble.
For number 3, I wasn't really sure if this will work, but I did it. It's that
yeah, number 3 was actually meant to be pretty easy.
the cube, it's kind of hard to explain. I think I'm gonna draw it. So gravity has a force of mg.
Uh-huh.
And so you do the standard breaking apart.
Mm-hmm.
Okay, and then I broke down this one again. This one doesn't count because it's not accelerating the cube. So if I draw it again. Then you can break it up to the horizontal vertical components again, because that will be the actual force on the object.
What do you mean actual?
Because this force here, it isn't accelerating the object.
Okay. First off, let's do this. So what's going on is that the cube is moving with velocity v, right? And this is constant. So not the cube, the wedge. The wedge is moving with velocity v, which is constant, right? So it's tempting to just switch to the wedge's frame. Okay, so if you switch to the wedge's frame, what do you have? First off, it's an inertial frame, right? Because the velocity of the wedge is constant. That means it's inertial, and you can apply all the Newton's laws and everything, right? Now, what about the block? The block originally was connected to the wedge, right? So they both were moving with the same velocity, right? And now the string is cut, but obviously the first moment the velocity of the block is the same as that of the wedge. So that means in the wedge's frame, the velocity of the cube initially is 0. Does that make sense? Okay, and then you don't need to actually overdo this. What you did here is almost all you need to do. So the block starts with 0 initial velocity and then just accelerates down with the acceleration equal g sine theta. Make sense? Joseph, you okay?
Yeah.
I hope that fact didn't knock you out. Okay, so, and then what else you need to do is to get this distance. Right, this distance, let's call it d. What you're given is this height, This is theta. So t equals h over sine theta, right? And then you just do regular kinematics, 1D kinematics. D is the distance to be covered, and this is the acceleration. So it's 1/2 at squared, which is 1/2 g sine theta t squared. Okay. And then you use this part of the equation and this part of the equation and solve for t. Do you see that? So t is 1 over sine theta times root of 2h over g. Do you agree, Joseph?
Yeah.
Yeah. So again, this was meant to be an easy problem just on your understanding of reference frames. Okay. So it's not like the next problem where the wedge is on the surface, so the wedge can move and accelerate. So in that next problem, the wedge is not an inertial frame. But in this one, whenever you see the mention that the wedge is being moved at a constant velocity, that makes it a perfectly inertial frame. You can do everything you used to do in just a lab frame. Oh, and there was a second part to this question. Find the value of this v such that the cube's velocity is perfectly vertical when it reaches the bottom of the wedge. Again, that's not too hard to do. Whatever your favorite way to find the velocity, you can, for example, use conservation of energy and find that v at the bottom is square root of 2gh, right? This is v at the bottom. And then the horizontal component of that needs to be equal to this big V. That's the condition for the cube to not have a horizontal component in the lab frame. Is that clear? In that situation, this V would kill the leftward component of velocity in the wedges frame. So the condition then looks V bottom cos theta, that's the horizontal part, equals V, which means that V has to be equal to the root of 2gh times cos theta. That's all. Vincent, I'm reading your question. What V? That's right, because yeah, exactly. So you switch to the wedges frame, and in that frame, things look as if the wedge was not moving, right? So this is precisely the case. In the second part, it matters just because you ask a question about lab frame, so you have to switch back. You have to use the V, but as long as you stick with the wedges frame, you don't feel its speed at all. As if you like ride in a car, the constant velocity, you don't really feel the car's velocity, right? It doesn't matter how fast it goes for all the experiments inside the car. Yeah, I would say this is more like a conceptual problem, not really too much to compute. Yeah, Alvin, it's problem number 3, not 4.
Yeah, I was talking about problem number 3, right? Because um, the block is gonna slide like to the left, right? To the left and down. So then that means like the momentum of the block is now going left. And then that means like if you were to apply conservation of momentum, then the wedge would be sliding to the right a little bit faster.
Well, the thing is, you're
But
explicitly given that the wedge is kept at a constant velocity.
yeah, so it doesn't mean like,
So, so
doesn't
you're
that mean just,
right. It wouldn't be possible if the wedge was left to slide freely. So implicitly, that tells you it's not sliding freely. It's being held, or it's being accelerated, like it's being moved by some additional force. And that force is exactly what would spoil conservation of momentum, because if you just say momentum is conserved, then you're absolutely right. The wedge would have to accelerate.
then since there's a force, then why is the frame inertial?
The frame is inertial just because the velocity is constant.
Hmm.
Right? That's what we call inertial frames. Frames that move with a constant velocity with respect to laboratory frame.
Yes.
Or zero acceleration with respect to the laboratory frame.
But then wouldn't actually, yeah, okay, I get it. All right.
Yeah, folks, again, numbers 3 and 4 are distinct. And I want you to feel the difference. So in 3, the wedge is artificially moved at a constant velocity. So Elvin is right. It requires some force. It won't happen naturally. So yes, there is a force. We don't really care about what it is, but it's there to ensure the velocity is constant. Okay. In number 4, there is no extra force, and the wedge is accelerating. So that needs to be, considered differently, because it's not an inertial frame. You have to do something else. I'll actually come back to number 4 after I finish with the theory of today's class, which will be center of mass, because I noticed Elvin tried to do something with center of mass, and also it's a good topic to begin with, but it would also help understand 4 and actually 5, I think, better. But let me go back to number 1, because that's probably the most challenging problem. And based on your submissions, Elvin got pretty close to the solution. Just need a couple fixes here and there, and I think you'll be able to finish it. So let's catch it. Okay, as we, oh, okay, well, yeah, let me also put what's given. Given the takeoff height is 7/4 of r. R is the radius. We need to find the mass ratio. Little m is the block's mass and big M is the ball's mass. So once again, as we established last time, the ball is actually not rotating. If you look at all the forces acting on the ball, gravity, normal, and the force from the block, which is normal, passing through the ball center, none of these forces can create a torque. So, and there is no friction here either. So the ball is not rotating. It just slides sideways. So it's pretty much as good as like I don't know, hemisphere or whatever. It just slides to the left. So then don't need to account for, say, rotational energy or things like that, or angular momentum. So we actually haven't studied that yet. So could have got suspicious if you thought that we might need it here. Okay. There are two ways to approach this problem. One is what Elvin did, and I'll actually come back to it. But first, let me present a more elegant method that, again, is related to switching to different reference frames. And don't forget about another problem that's coming from last class. That's another thing to use relative motion. Okay, so method one. Let's switch to the, okay, have to understand this carefully. So I'm going to switch to an inertial reference frame that moves with a constant velocity that is equal to the final velocity of the ball. Does that make sense? So let's say V, capital V, is the velocity of the ball when the block takes off. So I'm now considering a reference frame that moves to the left with V. Okay. Again, this is not Ball's reference frame. That would be non-inertial. It's a frame that moves with this specific velocity to the left. Okay. So why do I want to do that? Well, I want to use the result we got. Remember, we had a fixed hemisphere and the ball was sliding down. Looks like actually Vincent tried to kind of use that problem as well. So remember the result. In that stationary, so in that frame, when the ball takes off, the block takes off, the ball is not moving, okay? And we know that happens, so that happens when the component of gravity, G cos theta, theta is the takeoff angle. Yeah, let me mark that. Yeah. Yeah. I don't know if you can see it, but theta is the angle here. So G cos theta equals, let me call it U squared over R. So this is the centripetal acceleration of the block. Now, what is U? U is the velocity of the block in this frame. What do I call it? Let's say K. Does that make sense, folks? So U is velocity with respect to this reference frame. It's not with respect to the ground. But in that reference frame, we know this very easily, just copying from an older problem, okay? Do you remember this expression, folks? Okay, so that's the main reason to use this frame. Now, how do we get the U? Well, how do we get the mass ratio in? We're going to use conservation of momentum. Okay. And again, that's what Elvin did, but Elvin, you need to fix something there. You did not account for the masses. So P initial, yeah, let's see, on the x-axis, P initial equals P final. Now, what is P initial? Be careful. Oh, and this is in the laboratory frame. Let me see. No, in the same frame. Inertial frames are good enough, so all the conservation laws we had, they work there. So conservation of momentum in the same reference frame. So what is P initial? Initially, nothing is moving in the lab frame, but from the K perspective, they're actually moving to the right with velocity V. Does that make sense? So both of them. That means P initial is M plus M times V. Final, when the ball takes off, the ball is moving with the velocity V with respect to the ground. That means it actually stops in that special reference frame. So this is ball's velocity, but the block is having velocity M U cos theta. Make sense? Okay, finally, we need to do conservation of energy. And again, Elvin did this part correctly, I think. So the final the initial kinetic energy is, again, everything is moving with velocity v in that frame. So in that frame, the initial kinetic energy is non-zero and equal 1/2 total mass times v squared. The final kinetic energy, the ball stops and the block moves at 1/2 mu squared. Oh, and of course there is a potential energy change. So let's write that down. That means certainly here. That is mg. I can put r over 4, or I can put m. Oh, yeah, maybe I'll just put that. Okay. So this is UG initial. This is K initial for both. This is K final. Okay. So basically, this is it. Physics is over. Just do the math. So I guess I can just leave it for you folks to finish off. So this equation equation 3, equation 2, and equation 1. So you folks, do you think you can finish this? Yeah, just the math left. Another approach, And again, this is not exactly what Elvin did, but pretty similar. So method 2 is basically just use the laboratory frame. Then it's fairly easy to write energy and momentum equations. So use EBE, MBE, and derive V as a function of theta. So basically you solve for V from those equations. And that will depend on theta, okay? In fact, you'll get V squared of theta, but that's okay. It will be easy, I mean, to think of V squared of theta as a function. Now, the third ingredient here is the takeoff condition, right? So the reason I use this frame is because the takeoff condition was so simple in that frame. In the lab frame, it's not so simple. So instead, you could do this. You could actually think of this function and realize one important thing. What is so special about the takeoff angle? So this you can write for an arbitrary angle and solve for V. So this is for an arbitrary angle. And then let's understand what's so special about the takeoff moment. Okay, well, that's given. We need one more equation. That's what I'm saying. We need one more equation, and we're trying to get it. Oh, actually, let me fix it. What I wanted to write, my bad. Let me write V. So V is the ball's velocity. Yeah, now it should be easier for you. So imagine the ball, its velocity in the lab frame is increasing from 0 on. So what can you say about the takeoff moment? Folks, are you with me?
Are we supposed to like just derive this using momentum and energy conservation, or is this an observation?
When you say this, what are you referring to?
Like the special thing about V of theta.
No, I assume you've already used energy and momentum and derived the velocity of the ball
Right.
as a function of the angle. Again, this is still for an arbitrary angle. You just consider a random snapshot. The block is at some angle. You use conservation of energy and momentum, express the current velocity of the ball in terms of everything else, and that includes the angle. You don't use yet that this is specific value. Just keep it arbitrary for now.
It's like the sum of the ball's momentum, and I mean the sum of the ball's velocity and its own velocity in with respect to the ball. So, like, can you do something
No,
with that?
no, this is the ball's velocity,
Yeah.
not the block's velocity.
Oh, it should be like the opposite of.
I'm looking for a simple statement. Everybody can make it.
Oh, it's to the left.
We're in the lab frame, okay? We're in the lab frame. The block is sliding down. The ball is speeding up. What's so special about takeoff? Make a simple statement. Okay, guys, I'll give you a minute. Think about it. It's really very simple statement. Okay, any ideas?
Its velocity stays constant after takeoff.
Almost. I mean, this is correct, but it won't yet help us.
Oh, so is the maximum?
Here we go. Exactly.
Okay.
Folks, does that make sense to everybody? As the block is sliding, it's accelerating the ball to the left, but once it's taken off, that's it. It's not accelerating the ball anymore. So V of the ball is max. And now you'll see the reason why I wanted to keep theta variable. So that means that dv d theta, if you differentiate this function, or as you'll see, you'll actually get v squared here. So you can as well differentiate v squared, doesn't make a difference, and set it to 0. That will look a little bit messy, but then right after that, you will substitute cos theta equal 3/4, and everything will be pretty simple. Okay. I can tell you the answer, so you could check your work. Double check which way it goes. Yeah, in fact, the block's mass is larger than the ball's mass. It's 16/11. So folks, finish this off. You can submit an additional file, but I want you all get this because this is probably as hard as it gets, or almost as hard as it gets on sliding problems. You can make it harder yet if you have friction here and the ball is actually rotating. Then you would need to write down angular momentum and and rotational kinetic energy. But it's only basically math that gets more complicated. So these are the two methods. This is how you treat takeoff in the lab frame, and the way you treat takeoff in the balls frame is not the balls frame, but that special frame is straightforward. So I guess it's your call which method you use, but I want you to make sure you can do either one. Any questions about this? Okay, let's actually start new topic, and then we'll probably come back to number 4 or maybe 5. Okay, center of mass. Okay. There is a physical definition of center of mass, and we'll start with that, and then we'll get to the mathematical definition. So how many of you know the mathematical definition?
Like the weighted average formula?
I guess you can say that way, yes.
Is it like integral of x dm over m or something like that?
Oh, the distributed version, yes. Let's focus on, we'll start with point particles. Okay, so yes, this is the mathematical definition, really good. But who knows the physical definition of center of mass? Well, let me actually rephrase this. The two terms are distinct but often used interchangeably. Center of gravity. So near the surface of the Earth, these two things are equivalent, but far away or in strong rotational non-uniform fields, it's not. So what is the physical definition of center of gravity? Let me put it here. So if you have a distributed object, you can view it as a collection of point particles. And to each particle, there is a little force of gravity applied, and so on. So on average, you can think that there is a point somewhere where you have total mass times g applied. Okay, this is the physical definition. So the point where the average collective force of gravity is applied. And we'll actually abbreviate it as CM. Okay. Is, let me put it this way, imaginary point where the total force of gravity is applied. Now, tell me, why did I write the word imaginary?
Because it may or may not be on the object itself.
Okay, can you give me an example when it's not on the object?
Like two masses that are some distance apart.
Okay, can you give me a simpler example or nicer example?
A hoop.
A hoop or a donut. Exactly. So think about this. So, and I'll actually use red color for center of mass. So center of mass is somewhere here in the hole. So it's not on the object. Okay, I see some messages. Move around. Yeah, that works too. Very good. So now, how do we get from this statement to this formula? It'll take a few steps. So let's start walking there. First off, let's start with some simple shape. Oh, my camera is up. So let's start with a simple shape like this. So it's a rectangle, uniform rectangle. So you obviously know the answer. You know that the center of mass is in the middle. But let me show you how to get that using this physical idea. The idea is very interesting, actually. So let's use the fact that that the force of gravity is applied at some point. So if you suspend this sheet from a corner, you see it will hang like this. What does it tell us in terms of center of gravity? Where is it? Andrew, what do you think? Along the, exactly, Joseph, this is exactly what I wanted to hear. Yes, exactly. On the vertical line dropped from the pivot point. Because if it wasn't the case, then there would be torque created by gravity, and that would rotate the object. So the fact that the object is no longer rotating tells me that it must pass through through a line that goes to the pivot point. Okay, and you can actually draw that line. So for somehow I'm missing a pencil. Oops, not here. My electronic pencil. Actually, you know what? Why don't I draw it? So here is the so we say that let's call this point A, the corner from which I suspended, tells me that it's somewhere on this line. Now, how can I find exactly where the center of mass is on this line?
Hold it by another corner.
This one?
Like one that is not on the current diagonal.
Like this. Okay, and then I draw another line. So let's say this is point B. And then where they intersect should be the center of mass. Now, what if I start suspending from various points, like random points? Is it obvious to everybody that all the verticals dropped from those new points should all intersect at the same point at the center? So this is an important feature of center of mass. Obviously, for the purposes of finding it, you only need 2 lines. You don't need all of them, but it's good to know that all of them will intersect at the same point. And this is a constructive way to find center of mass. You're given a random object, you just suspend it from one pivot point from another pivot point, find where those verticals intersect, and here we go. That's where center of mass is. Okay. Now, we're still pretty far from this formula. Let's make another step in that direction. So as Alvin suggested, I'm going to consider point particles. And the first example is 1 point particle. Then it's obvious that the center of mass is at the particle. It doesn't have any size or shape, so it's right at the particle. Now, what if we consider 2 point particles? One here and one here. Without loss of generality, we can assume that they're on the x-axis. And then what I just did, I connected them with a massless rod. Now I made everything connected. Okay, and I can use the previous method. Okay, folks, you're with me? Okay, now one way to suspend it is obvious, just by one of the ends. If you do that, you'll find that the center of mass is somewhere on this line. Okay, good to know. Let's write it down. So center of mass is on the line, and you can probably even tell it's between the masses. Okay. It's interesting if you start allowing negative masses, then the center of mass will be outside. Maybe we'll revisit that one day. It has a pretty important geometric consequences. And if you are participating in math Olympiads, there is a powerful method in geometry based on center of mass. But let's discuss it some other day. Now, what do we do to actually find out where the center of mass is exactly on this line? We cannot suspend from the other end. It will just tell us the same thing. So we need to find a pivot point somewhere such that when we suspend it from a string, or if, say, you put a finger here, so you put a finger here, everything is balanced. Okay, so let's call this mass M1, this M2, and also introduce the distances from here, I'm going to call them L1 and L2. So given M1, M2, and L, the total length that you can use as a unit, find L1 and L2. So first off, you know the rule of lever, right? Yes, Alvin. Technically, I'm kind of invoking torque here, but I'm trying to avoid this word until we officially learned it. So I'm saying things like rule of lever, such that the force times the arm length, right, equals the force here times the second arm length. So that results, let me write it down, rule. M1 L1 equals M2 L2. Okay. And obviously can write another equation for the known L's. L1 plus S2 is equal L. Okay, folks, why don't you take a minute and derive what L1 and L2 are, or at least L1, and feel free to put it in the chat. Okay, I got two answers. They are the same and they are correct. Okay, good. So L1 equals L times M2 over M1 plus M2. And I'm not sure, Alvin, if you actually derived L2 or did some simple trick. So if you look at this answer, you understand that the answer should be symmetric around 1 and 2. So whatever you got for 1, you can swap indices 1 and 2 in the answer, and that should give you L2. So this becomes M1 and this becomes M2 plus M1, but of course you don't need to worry about the denominator. So this is it. This is how you compute the position of center of mass of 2-point particles. And notice one interesting thing. The distance is inversely proportional to the mass. So that means the center of mass is closer to the heavier mass, which again should make sense to you, right? The more, like, center of mass should be closer to where more mass is concentrated. Now let's work out an example with 3 masses. So now you know everything about 2 masses. Let's see how you can handle 3. These are 2 light rods connecting 3 particles. M1, M2, M3. Each rod's length is L. You can use that as a unit. And the masses are 1, 2, 3 kilograms respectively. So what's the idea? We know how to handle 2. We can find center of mass of any 2 particles. And here comes a very important idea that if you combine two or actually more particles onto their center of mass, that does not affect the position of the overall center of mass. You guys catch that? So you take, say, two particles, combine onto their center of mass, and this rearrangement does not affect the position of the overall center of mass. Yeah, exactly, Alvin. So that allows us to like treat 2-point particles at a time, because we know how to do two. So Alvin suggested the following plan. Combine M1 and M2 onto their center of mass. Leave some space here, we'll insert the step. And then consider center of mass of 1, 2, okay, and M3 as 2 particles. And just basically repeat the same idea. So, well, let's do that. So where is the center of mass of 1 and 2?
It's at a point between M1 and M2 that splits it into a 2-to-1 ratio.
Okay, so Vincent wrote 2/3 L, and this is probably the best way to say this. Exactly. So this blue dot is CM12. And yeah, let's indicate where it is. So this blue distance is 2/3 L. Now we consider this point and the remaining particle. So we got 3 kilograms here. How much mass is sitting here?
3.
3. That's the idea, right? We put all the masses onto one point. So now there is 3 kilograms. Okay. We'll need this distance. What is this distance? Yes, 4/3 L. Thank you, Joseph. Now, where is the center of mass of these two guys? Now I'm going to use red because that's the last step. Middle of this, I assume, right? Okay. So yeah, let's just be careful. So this is the overall center of mass. And it's helpful to actually know this distance from the leftmost mass to the overall center of mass. Yes, so this is 4/3 L. And let's put that as an answer. 4/3 L from M1. Okay, folks, this works, but you probably have a question. Why did we discriminate? Why did we leave M3 behind in the beginning? Could we actually say combine M2 and M3 first, and then consider the leftover mass M1? Could we do that? Do you think we would have gotten the same answer? Okay, how about combining M1 and M3 first, and then M2? Would that be equivalent? Okay, well, let's split up. Let's say based on how I see you on my screen. Then, in fact, we can take a break, but during the break, I want you to do this little exercise. Vincent and Andrew, you combine 2 and 3 first, then M1. And Alvin and Joseph, you Combine 1 and 3 first, then M2, then M2. Okay. And at the end, I want you to find the distance from M1 so we could compare the answers. Okay, so let's take a 10-minute break. But by the end of the break, I want you to report your answers, okay? So now if you do rule of lever, the L from this end should be this mass divided by the total mass times the distance. Okay. So let's say L1 now would be 8/5 L times 5 over 1 plus 5. So what do we get? Fifths cancel, 8 over 6, which is 4/3.
Can we generalize this inductively, or
You mean for more particles?
yeah, for like more particles? Yeah.
Yes, of course. So we can say, well, sometimes you may want to be more efficient. For example, if you have 4 particles, you probably want to combine 1 and 2 and 3 and 4 in one shot and reduce the number of particles by a factor of 2 right away. But again, worst case scenario, you'll be getting rid of one particle at a time by combining. Okay. But now we're ready to, sure, maybe here. Now we're ready to use Andrew's expression that he put up early on. So yes, in some sense, the center of mass is the average position of center of mass. So I'm going to use capital X for any, like, and in fact, I'll be using capital letters for anything related to center of mass. So it's easiest to remember this formula from the bottom. The bottom, you have the total mass. N is the number of particles. And on top, you have mass times position plus m2 x2 plus so on mn xn. This is, I'm going to call equation start. And you can use it for the three particles we just did. But you need to first, of course, explain what your coordinate system is. So to be consistent, you might want to choose this as your axis. And this is your origin. So this is 0, this is the x-axis. Then x1 is 0, x2 is L, and x3 is 2L. Okay, and then plug and check. Here you have 1 plus 2 plus 3. On top you have 0, 1 times 0, plus 2 times L, plus 3 times 2L. If you substitute it all, you should get the same answer, 4/3. But I want you to know that this formula actually follows from these considerations. So if you allow an arbitrary choice of origin, which this formula is, right? And this formula works no matter what origin you pick. Okay. Let me talk about two important features here. First off, we already talked about how you can combine two or more actually particles at once onto their center of mass, and that doesn't change the answer. Let's see if this formula satisfies that requirement. So what does it mean to combine particles? Let's say if you combine particles 1 and 2, what does it mean for this formula? In fact, all you need to do is to put parentheses. Here it's obvious, right? You're just replacing two separate particles with one of the total mass of 1 and 2. That's trivial. Now let's look at the combo in the numerator. What is this? In fact, this is nothing else but x12, the position of center of mass of 1 and 2, times m1 plus m2. Do you see that? Think of this formula for only two particles. Then it will become obvious. But what does this represent? This represents that you take a particle of this mass and place at this position. Obviously, putting parentheses here doesn't affect the answer. Just that simple, okay? So this formula by construction satisfies this important feature, the combining feature. question to you folks. What happens to the position of center of mass if I double every mass? Nothing, well, doesn't change. The position of center of mass doesn't change. That's right. So that's easy to see from the formula, right? You put the factor of 2 everywhere on top, everywhere on the bottom. Obviously, they cancel. But now I want you to think physically, from a physics perspective. Pretend that you don't know this formula. Right? It's not there, okay? So it's gone. Let me rephrase this question. Let's say you did not double the mass, but you multiplied every mass by a factor of 2.2. Why shouldn't center of mass change? Why such a weird number in the first place? Yes, Alvin.
It doesn't actually matter like the number you multiply it by, because like in a sense, like the two situations are like similar, like, quote unquote, because
Yes,
you can
yes,
just kind of
yes.
scale it.
Why did I pick this weird number, 2.2? What is that about?
It doesn't matter what number it is.
You're right, but that's not the reason why I picked this specific number. This number is not random. Folks, what is that number about, 2.2, in regards to mass? Okay, that was meant to be a quick question. This is the number of pounds in a kilogram. So, do you see where I'm heading now?
Units don't matter.
Exactly. Or let's say units matter, but different choices of units should not affect the answer. Let's say you have a bunch of masses, you found their center of mass, and then all of a sudden you decided to measure those masses not in kilograms, but in pounds. On the math side, that would result in multiplying every mass value by 2.2, right? But on the physics side, who cares? Who cares what units you use to measure the masses? The center of mass is a specific location. Doesn't matter what units you choose to describe the system. Does that make sense? So this is it. So in fact, I want to use this. I want to use this idea of units to demonstrate that this formula makes a lot of sense as to that it's invariant under rescaling of masses. Okay, so from now on, I want you to just stick with this formula. My theory is that once you've written a formula 5 times with your hand, you memorize it, you have muscle memory. So this is the first time, and we'll write it a few more times. So first, I want to talk about generalizations of this formula. You can write similar formulas for y and z positions. I'm not going to write it down, but you probably want to. What I will write out is the vector version. Think of the capital R as the radius vector of the center of mass then that can be written as M1R1 plus M2R2 plus so on MnRn divided by the total mass. 1 plus M2 plus so on Mn. Now you can allow the masses to move so that these R's depend on time. And you can take time derivative of this. Then what do you have on the left? On the left, you probably want to call it the velocity of the center of mass, right? What do you have on the right? On the right, it's also pretty straightforward because the denominator is constant. Yeah, we assume constant masses. That's important. All the masses are constant, so the denominator is just a factor. And then when you differentiate the numerator, you differentiate the R's. And when you do so, you get the corresponding velocities, right? So what you can write is this: M1 V1 plus M2 V2 plus M3 V3 or Mn Vn over M1 plus M2 so on Mn. Let's take one more time derivative as we're on it and write the acceleration of center of mass equals M1A1 plus M2A2 so on plus Mn An over the total mass M1 plus M2 plus so on Mn. That's been 4 times. Okay, one more time to go. Let's look at the second equation. You can probably recognize very easily that this is what? Yes, this is momentum. So let's look at equation 2 and write P1 plus P2 and so on plus Pn over the total mass. Yeah, let me call this M total, big M. Then I can rewrite this as follows. I can rewrite it as total mass times velocity of center of mass equals, and this is nothing else but the total system's momentum. Okay, so how do we read this equation? Think about this. You have a bunch of particles moving, so they have some total momentum in some direction. So you can probably think of visualizing that system as a single effective particle having that same total momentum. So the question is, okay, it's easy to think about the mass, but what would be the velocity of that particle? And here is the answer. It should be the center of mass velocity. So center of mass velocity is the velocity that a single particle of combined mass should have to give you the system's momentum. Okay? So, or you can say this is how you find the total momentum of the system. Just multiply the total mass by the center of mass velocity. If you look at the third equation, you recognize that these are forces, the net forces acting on each particle. And if it happens that the total net force is 0, then acceleration is 0. Okay, so look at equation 3. If the system is isolated, then external forces are absent, but the internal ones are here. And as we did the last time, remember how we summed all those internal forces? They just zero. So F net 1 internal plus so on F net n internal, this is 0. And acceleration of center of mass must be 0. And again, the only assumption we made is this, that the system of particles is isolated. Now, what does this mean? This means that velocity of center of mass is constant. Let's make one more assumption. Assume that the initial velocity of center of mass was 0. From that, we know that velocity is constant. That means it must stay 0 forever, right? So V is just 0. Okay. And that implies that the radius vector of center of mass is constant. So that, in other words, the center of mass doesn't move. Okay. So we made two assumptions. The fact that the system is isolated and the initial velocity of center of mass is 0, and we concluded that the center of mass must not move. And again, in general, that means your particles may be moving like crazy, right? Individual motions are not restricted, but the center of mass must stay at the same place. So let's is everything clear on this slide? Okay, let's work out a couple problems here. First, a baby problem, and then something much more interesting. So let's say the elder brother is teaching his younger brother how to swim. Feel free to criticize his teaching methods. He's using a very long stick, massless stick, whose length is 3 meters. Given LS. The masses of the kids are also given. Say 60 kilograms and 30 kilograms. Now the guys start pulling on the rod in some random manner until they meet. So the question is, where do they meet? Where will they meet? And again, you probably can tell me the answer right away. It takes like 90% of the problem to argue why it's the answer. So maybe first tell me the answer and then we'll convince ourselves it's true. Okay, I see something in the chat. At their center of mass. And where is it? 1 meter from M1. I like the symmetry. 1M from M1. Yeah, so this distance is 1 meter indeed. Okay, so let's put that as the answer. Now let's argue why this is true. So who wants to do that? In the spirit of the previous slide. You guys want to switch back to the previous slide? Are you good?
So the velocity of the center of mass started out as 0, and there's no external forces, so it's still going to be 0. And then, you know, if they were to meet, then the center of mass would stay in one place. But then if you move the two masses together, then they become one mass, and the center of mass of one particle is that particle. So it has to be there at the center of mass of the original two.
Okay. When they meet, x final equals x1 equals x2, right? They're all at the center of mass. Well, that kind of makes another implicit assumption, that the kids can be treated as point particles. And is that a reasonable assumption?
Well, you can just take the center of mass of each person.
Yeah, I mean here, when they meet, you're saying that they are at that very position. Both kids are at the same position. So that is a reasonable assumption if their size is much less than that of the rod. Okay. Again, it may be reasonable, but may not be reasonable. You know, kids these days can be pretty big. Okay. Yes, this is pretty much it. Just need to maybe elaborate a little bit more on why this is true. So you consider all the forces acting on all the kids and argue that they either cancel or negligible. So maybe let's just do it real quick. So there are gravity forces down, buoyancy forces up, but they're vertical. We don't really care about the vertical forces. On the horizontal, you may have an issue with the drag force. So you have to make probably yet one more assumption that the kids are moving slowly and use the fact that drag force is proportional to speed. So if the speed is small, so is the drag force and can be neglected. Okay. So just need to elaborate here. I'm putting a comment, but actually I wanted to compliment to Alvin's homework. You always reason things in very much detail. So this is the way to go. Vincent, you may talk to Alvin about it. You're very concise all the time. So make sure to insert words in your work. Okay, so let me actually take this problem to the next level. And some of you may view it as a life tip. Okay, it's a problem about Romeo and Juliet. I'll probably assign it as a bonus question because I actually want to revisit one of the previous homework questions. Okay, so Romeo wanted to know something that he didn't dare to ask Juliet directly. What do you think it was? Yeah, that was Juliet's mass. He didn't ask, he didn't dare to ask her. So he decided to, he designed a whole plot to figure it out. So he invited her on a road trip, on a boat trip, and did some homework. So here is the boat. Here is Romeo sitting at the left end of the boat. And here is Juliet sitting at the right end of the boat. So what did Romeo do? He measured everything he possibly could. So he knew the length of the boat. He measured his own mass and the mass of the boat. But obviously that's not enough because it has nothing to do with Juliet. But let me give you what he measured. M1 was 70 kilograms. L was 3 meters. And the mass of the boat was 30 kilograms. Okay. Watch, guys. You may need to you may need this trick someday. So now Romeo goes, Juliet, the sunset is so wonderful from my position. Would you like to switch places? And she buys into it. So tell me what happens. Ignore all the vertical movement. What happens horizontally?
The center of mass takes on some velocity. Do they move at like the same velocity towards each other when they make the switch?
You're thinking too deeply. It
Okay,
actually doesn't matter.
Then the center of
Tell,
mass.
like when they switched and sit at the new places, what would it look like? What should I draw? I was about to joke that Joseph went on a boat trip. What happens to the boat? Okay, forget Juliet for a second. Suppose Romeo is the only person on the boat and he moves to the right. What happens to the boat? Yes, it moves. Ignore the tilting. Ignore the vertical motion. So the boat moves. Where does it move? Which way? Exactly. Now, suppose Romeo was not in the boat, was only Juliet, and she moved to this end. What would happen? Okay, opposite. So if Romeo moves, that tends to make the boat move leftward. If Juliet moves, that makes the boat move rightward. Who wins? What is the overall movement of the boat? Again, you have to make an assumption.
Like opposite of the direction of whoever has the greater mass.
Yes, and we're making an assumption, which we'll test by the math, that Romeo is heavier than Juliet. If you remember, he was 3 years older, so it may not be unreasonable. Okay, so let's draw the boat a little bit to the left of where it was. So here you have Romeo, and here you have Juliet. So what Romeo did, he also measured the displacement of the boat. Yeah, he was hiding a ruler in his pocket, and he measured this displacement. And it turned out to be 30 centimeters. So based on this information, I want you to find Juliet's mass. And that would be a homework question. Okay, so let's go back. Did we lose somebody? Okay, let's go back to problem number 4 from the homework. Let's see what it is. Okay, let me actually show you this picture. Oh, so this is way to do it. Okay, folks, what do you see? Do you see whiteboard still?
Yeah.
Okay, I'm not sure how to make it work, but
Is there something else we should be seeing?
I tried to share a portion of my screen, but I guess I'm not exactly sure how to make it work. So let me maybe just draw it. Oh, okay. Have a better idea. Okay, do you see the diagram now?
Yep.
Okay, here we go. So this is to problem 4. In bold, you see the original situation. Now the block is not fixed and it can slide without friction across the floor. Now the cube is kicked up with velocity v naught. The question is that there are 2 questions. How long does it take for the cube to slide back down to its original spot on the wedge? And what was it? Something about final velocity, I guess. Let's double check. Yeah, what's the final velocity and how long does it take? So there are 2 ideas that come in here. First, you realize that the external forces only act on the vertical. That clear? There is nothing horizontal. That means the center of mass of the system moves horizontally with a constant velocity. So F net x is equal to 0. So what we just discussed about like an isolated system, the system doesn't have to be totally isolated. It may be isolated in one dimension. then in that dimension, you could say momentum, the center of mass moves at a constant velocity in that particular dimension, which is the x dimension in this case. So you can say that Vx is constant. And what is it equal?
V naught cosine alpha.
That's not quite right, though. So this is just the cube's velocity. Oops.
Oh yeah, you divide by 2.
Trying to get to the chat. Yes, divide by 2. So Vincent, can you explain? Or can you not talk? You only can type.
I think it's because you're talking about like conservation of momentum afterwards. Like before, it's because they have the same mass afterwards, there's 2m, so the velocity will be reduced by 2.
Or that. Yeah, you can either talk momentum or you can just recall that center of mass velocity equals m1v1 plus m2v2 over total mass. Now v2 was 0, right? And the masses are equal, so this ratio gives you half. Okay? So this is the center of mass velocity. That means, now imagine that, so you kick the cube up, it slides up, they move together, then the cube slides back down, and the moment it got back to the original spot on the wedge, this is the picture, the punched picture, okay? So they just basically have displaced as a whole by a certain distance s. But what is this distance? This distance must be equal to the center of mass velocity times time, the time that you're trying to find. Make sense? Now let's compute s using some other consideration, and then we'll set it equal and solve for t. Now look at this axis. So this axis is not, so this reference frame is not the wedge's frame. It's similar to problem 1's trick. So this is an axis that's parallel to the incline of the wedge, but this is a stationary frame. Is that clear? So this is a stationary axis that's not moving. This frame is not moving with the wedge. It's just the axis is parallel to this. Now, as the, so wedge, the problem with the wedge, as we already discussed today, is that it's non-inertial. It's accelerating, right? But think about the force acting on the wedge from the cube. Which way is it? Folks, that's a simple question.
Wait, were you talking about the force from the block to the wedge?
Yes. You're breaking. Is it just me?
Well,
So folks,
it should
yeah.
be to the right.
Oh, well, the force is normal, right? This is a normal force.
Yeah.
It's easiest to think about the force from the wedge on the block. It should be normal, like this. But the force from the block on the wedge is equal and opposite. So the bottom line here is that the force is perpendicular to this axis. Okay, so the force on the wedge is perpendicular to the x-axis. You see where I'm going with this? That means along the x-axis, this frame, the wedge's frame, is inertial. Okay? So wedge's frame is inertial along the x-axis. Okay, and that's basically an argument that allows you to do the standard kinematics along this tilted axis. Right, so what is the acceleration? What is AX of the block? This is simply the parallel component of gravity. Right, G sine theta, well, negative G sine theta because it's against the x-axis. Alpha, I guess, G sine alpha. Does that make sense, folks? Even though the wedge is not inertial, but on that particular axis it is. So we can still use the old stuff. And then the rest is really straightforward, right? What is the time? Or what is the S, rather? What is the S? You can find x1. X1 is S times cosine alpha, right? But x1 is also equal 1/2 AX t squared from the kinematics. So if you now put it all together, what do you get? You get 1/2. Sorry. I guess I need to put V initial X times time, right? We should not forget that. So X1 equals V naught T minus G sine theta times 1/2 T squared. And on the other hand, it's equal S cosine. Why do I keep writing theta? Alpha. Okay. So 1/2 V naught cos alpha squared times T. And then you can solve for T from here. Does that make sense? Folks, do you follow? You know how to finish this? Okay, why don't you finish this and submit in addition to what you already submitted? Okay. So you got a couple standing problems, the new problem about Romeo and Juliet, and I'll probably assign some more, just for those of you who already finished most of them. Okay, any questions? Then let's call it a day. Oh, and I may not be able to meet with you like the week after next, but I'll get back to you on that.
Is that Thanksgiving
So-
week?
Yes. So Thursday would probably be off anyway, right?
Yep.
But I'm not sure about Monday. I'll let you know. Okay.